Okay, some solved problems for chapter 44. First, we're going to have a neutral pion that's going to decay into two photons, and we're looking for the energy, frequency, and wavelength of each photon. Some keywords to pay attention to is this pion is initially at rest, so the only energy it's going to have is going to be equal to its rest mass. So the energy of the pion is going to be equal to mass times c squared. And we do know, if you check out the hint, it says look in section 44.1 for the mass of a pion. We know that the mass of a pion is going to be 270 times the rest mass of an electron. So you go ahead and you look this guy up, and it's going to be 0.511 mega electron volts. So the energy up for grabs is going to essentially be 138 mega electron volts. Now, one thing to keep in mind is each photon is going to get half of that energy, and also energy will be conserved as well as momentum, so these photons are actually going to go in opposite directions. So the energy that each photon will get is going to be exactly one half of that, so we're talking about 69 mega electron volts. Now it's pretty straightforward. We're just going to come back to our old friend, E is equal to h multiplied by frequency, and so from there we can say that the frequency is going to be equal to the energy divided by Planck's constant. So we've used this guy quite a bit. So the energy is going to be 69 times 10 to the 6 electron volts. Go ahead and divide that guy by Planck's constant. I'll use the one in electron volts. 4.136 times 10 to the negative 15th. And we type that in, we're going to get 1.67 times 10 to the 22nd with a unit of hertz. And last but not least, we're looking for the wavelength. So the wavelength is going to be c divided by that frequency, or 3 times 10 to the 8th, divided by 1.67 times 10 to the 22nd. And we're going to work our way out to about, that's actually going to be 18 femtometers, where a femtometer is 10 to the negative 12 meters. Now, what region is this in the electromagnetic spectrum? It's going to be in the gamma ray region, and gamma rays have lots of energy, so kind of makes sense. Now let's take a quick look at a collision inside of a collider with an electron with some kinetic energy that's going to run into a stationary positron. So here we have our electron. It's going to, have our electron, that's the negative one. It's going to run into a positron that's just kind of sitting there. So what we kind of do is we say, well, what's the available energy? What we're looking for is this guy right over here. Keep in mind that the rest mass of an electron is just 0.511 mega electron volts, and that's far, far, far less than the 20 gigavolts that is available to it. So that guy's pretty much negligible, and as long as the energy is much, much greater than mc squared, we can boil it down to this equation right over there. So that's one we're going to use for this example right here. So the energy that's going to be available to the system is just going to be equal to the square root of 2mc squared. So that's going to be 2 times 0.511 times 10 to the 6 electron volts, multiplied by the 20 times 10 to the 9th. And we're going to work our way out to about 143 mega electron volts, and that is available to the system. Now, if these guys were accelerated in a collider, what total energy corresponds to the same available energy in part A? Well, you could convince yourself that if these guys were accelerated in a collider, then each is going to get half of that energy because they have the same mass and all that good stuff. So they're each going to get 70.5 mega electron volts. You add that together, and the total energy is going to be twice this, or 143 mega electron volts. Okay, let's take a look at problem 44.15. We have a K plus meson that's going to decay into 2 pi mesons, and we're wondering, first of all, which ones can it possibly be, and then the kinetic energy. So let's take a look at table 44.3. Here's my K plus meson. There's the mass. We're going to use that in part B because the mass will be converted to energy. And we note that it has a charge of +1, and something we know is charge has to be a conserved quantity. So we take a look at our 3 possibility for the pi mesons, and note that the combination has to have a charge of +1. The only one that it could possibly be is going to be a pi plus and a pi 0, and you can convince yourself that the pi minus just simply wouldn't work, because at the end of the day we need to have a charge of +1. So this is the only possible combination right here. Now let's find the kinetic energy. The kinetic energy is going to come from the mass difference, and so what we essentially have to do is let's take the mass of the K plus guy and subtract the mass of the pi 0 and the mass of the pi plus meson, and what that's going to do, this is essentially going to give us our mass difference. And take a look at the table. We can read off the mass differences: 493.7 mega electron volts multiplied by, or mega electron volts per c squared, minus 135 mega electron volts per c squared, minus 139.6, also mega electron volts per c squared, and therefore our mass difference is going to be equal to 219 mega electron volts per c squared, and then E is equal to mc squared tells us the energy that these guys are going to have is going to be 219.1 mega electron volts. Keep in mind that they're not going to share this energy equally, because they don't have equal masses. One had 135 and one had 139.6 mega electron volts per c squared. Now let's play around with some quarks, and following 44.27 we're looking for charge, baryon number, strangeness, charm number for the following combinations, and I add a little table for name just for fun. So all we're really doing is we're taking a look at this table right over here, and we're looking for quark UD and S. So this can be essentially a U plus a D plus an S. So the charge is going to be 2/3 E minus 1/3 E minus 1/3 E, and that's going to give us a charge of 0. Baryon number, that's going to just follow it in the table. It's going to be 1/3 plus 1/3 plus 1/3. It's going to give us a baryon number that's equal to 1. The strangeness is going to be 0 plus 0 minus 1, and so that's going to be a strangeness of -1. And the charm is going to be 0 plus 0 plus 0, and it's going to have no charm. And we'll come back to the names and I'll finish those at the end of the day. So keep in mind that the values for U bar is essentially going to be negative of those for U. So the charge, here we have the C, it's going to be 2/3. And then a U bar is going to be -1/3, so minus 2/3, and this thing is also going to have a charge of 0. The baryon number is going to be 1/3, and it's a U bar, so it's going to be a minus 1/3, and the baryon number is going to be 0. The strangeness is going to be 0 plus 0, it's going to be a 0, and the charm is going to be +1 plus 0, and it's going to be +1. DDD, I'm going to go ahead, and there's my D, and I'm just going to hit it 3 times, and the charge is going to be negative that of an electron. The baryon number is going to be 1/3 plus 1/3 plus 1/3, and that's going to be +1. The strangeness and charm are both going to be 0 plus 0 plus 0, 0 plus 0 plus 0. And lastly, DC bar. Again, the C bar just means we put a negative in front of everything. And so it's going to be essentially -1/3 minus 2/3 E, and that's going to give us a negative E. The baryon number is going to be 1/3 minus 1/3, so that's going to be 0. The strangeness is going to be 0 plus 0, which is going to be equal to 0. And the charm is going to be 0, don't forget the negative, it's going to be 0 minus 1, it's going to be -1. Now for the names, I like this hyperphysics. If you just Google meson, I think meson table or meson something like that, hyperphysics will pop up, and we can just kind of go ahead and look at the makeup of these guys and see if we can identify the names of these, just because it's kind of fun. I'll let you poke through that. You may have to go over to the baryon table for some of these, so you can kind of see that. Here's our DDD, that's going to be a delta or a delta minus, and I'll just kind of fill out the table and let you convince yourself of it. And here I've gone ahead and now I have all the names filled in appropriately. And last but not least, let's just use Hubble's law really quickly. The only thing to pay attention with Hubble's law is just pay attention to the units. Hubble's law says that the speed of a galaxy is related to Hubble's constant multiplied by how far away that it is. And here we know what that is 50 to 10 mega light years. So pretty straightforward. We're going to say that the speed is going to be equal to Hubble's constant, which is going to be 71, and that's going to be kilometers per second per megaparsec. Keep in mind that 1 parsec is 3.28 light years, so we're essentially going to say that 1 megaparsec is going to be 3.26 mega light years. So just kind of kept my mega in each one of those, and then we're going to multiply this guy by 50 to 10 mega light years, and that's this guy right over there, and all the megas are going to work themselves out, and we're going to wind up with a speed that's going to be equal to 1.13, a couple more digits here, times 10 to the 5th. The only thing to be careful of is that this is going to be kilometers per second. So kilometers per second, here we've got my kilometers per second just right there. Let's go ahead and convert this into something that's a little bit more palpable for the next part of the, or for the next thing. This is going to be 1.13 times 10 to the 8th meters per second. So that's going to be equal to the speed that the galaxy is receding. And it is receding, so it is red shifted. If it was coming towards us, it would be blue shifted. And for port B, we're just kind of looking for the ratio, so we're kind of turning to this guy right over there. So we're looking for lambda naught to lambda sub s, and that's going to be equal to the square root of c plus v and c minus v. And I'm just going to be kind of lazy. I'm going to realize that there's 10 to the 8th on the top, 10 to the 8th on the bottom, and I'm just going to leave that guy alone, 1.13, and this is going to be 3 minus 1.13. You go ahead and take the square root of that guy, and it's going to be shifted by about 50%. 1.489 is the ratio.